topic that we just wrapped up is the solving differential equations. Solving differential equations, to be clear, of dimension one. So not systems, right? So it was as if we went back to chapter one. Okay, so we have been doing, and now we're back. We're back to the systems. So once again, to the systems, meaning this, x prime is equal to f of x. Okay, linear system. So linear system for these. Okay, that's what we done before, and that what forced us into this. If you remember, they stopped. It forced us into take this whole thing up and do the complex numbers. Okay, so because we realized that the directions are the eigenvectors are important, and to find them, this is how you find them, and then sometimes you end up with complex eigenvalues. Okay, so that's how it happens. So eigenvectors. What are they? And then that gives me we need to find eigenvalues. And then what if they're complex? And so that led us to the whole complex algebra, complex calculus. Okay. Algebra of complex numbers as well as complex calculus. Okay, so nonetheless, so now what is that? So what's the how do complex numbers appear if is there a direct way? So that was a roundabout way to get to complex calculus, but can we now feed it back into our system other than this direct route? There is some. So x and y, once we understand that there is a complex algebra and complex calculus, we can do this ODE could also be complex. So if we here in a real environment, we have x is equal to xy, okay, xy real. Now, and f is a, b, c, d, also a, b, c, d real. Or we can do the same, and now we just do everything is complex. Same exact story. And so this is complex. Okay, so xy is made of two complex numbers, and it's still a vector, but its components are complex, and the matrix is also made of complex numbers. So it's totally possible. And naturally, if you look at some practical applications, you cannot see complex. The values cannot be complex. Time is not complex. The values are, well, I don't know, temperature, electricity, whatever that is. We looked at just recently. Velocity. None of these quantities is complex. They're all real. Okay, so then the switch is really just a matter of convenience, which sometimes really is so significant that is worthwhile. So even though we're not really going to elaborate on that, but let's review then what a complex a complex version of the same theory would look like. Okay, so linear. So complex linear algebra. Complex linear algebra. So everything is pretty much the same, and what we're after is we already had it, and we just one part of the classification theorem of quantum linear operators. We already had it. The option when the discriminant is negative was not was actually provided, but not elaborated. Okay, so now we have a better interpretation of it because now this negative discriminant gives us complex eigenvalues, and what does it tell us about the linear operator? Okay, so all right, so this one just to refresh your memory. This is how it happens. We have a linear operator which is rotated by 90 degrees. And then if you go through the motions and evaluate our characteristic polynomial happens to be determinant of this matrix, L squared plus 1, we solve it. The characteristic equation produces two complex imaginary solutions plus or minus I. Okay. So all right, so the eigenvalues are imaginary now, so there can be no real that's the thing. There cannot be any real vector the that value of which is complex. Okay, so you start with a real number. Remember what this is supposed to produce. It's supposed to produce AB is equal to lambda V. Okay, so if V is real and lambda is not, say plus or minus I, so plus or minus IV, it is not real. Okay, so then that's the thing about it. The fact that there are no eigenvectors in this situation when the discriminant is negative, that's what does that mean? It means that they're still there. They're complex. Okay, so all the eigenvectors are pointing in that extra direction, which by the way remind us that the situation we're dealing with is actually four-dimensional. So okay, so remember that differential equation we started with, we had one input variable, okay, and the one output variable, and here we have the input variable is still one, but the output is now complex vector, each of which is complex. Altogether, it is 4. Okay, so well, that's what it is. So just to remind you that the complexity has been growing, but sometimes it's actually simpler if we understand that complex numbers are just numbers and we deal with them just a bit more numbers. Now let's just go through this and let's just find the eigenvectors as if we exactly the same way we've done it before. So this is my matrix happens to be real, but we ignore that. Now xy is now complex. Okay, so these are complex. So there are no real eigenvalues. So that's really the conclusion we understand right away. So the fact that before we said there are no real eigenvalues. So just because we now willing to deal with complex eigenvalues doesn't mean that there is we can the eigenvectors can remain real. Multiply a real vector by a complex. Now we have a complex vector. So it means that there is no it's not a multiple. Okay, so which is we can see how that works out with this simple example. So I is my eigenvalue, so xy multiplied by I end up with two equations: negative y is equal to ix and x equal to iy. Okay, so cannot x and y cannot both be real. That's the thing. So for example, if x is real, then y is imaginary, right? And vice versa. So hypothetically, it surely can work out. Let me give an example. So if x is equal to 1, then y is equal, hold on, this is working out, x is equal to 1, y is equal to negative I, and it still does not work out. Is it working out? Y, no, it's still not working out. So let's just say the negative conclusion is that there are no real eigenvectors. So that requires us to actually proceed if we want to understand these eigenvectors in the complex directions. We have to understand them. We have to have a complex linear algebra. Okay, so matrices, that's what the complex vector looks like. It just, once again, it has two components only, but each is a complex number. Okay, such as this. Okay, so the complex vector then has two, like I said, the total is 4 dimensions. Okay, so 1 for the first component of the vector, so 2i, this is the 2i right here. 2 plus i, a real part is 2, imaginary I, and 1, and then the second one is here. Okay, so it's -1, the real part, and 2i is the complex, imaginary part. Okay, so this is over here is one single vector. One single vector is right here. Okay, so two points on the two complex points. So once again, it looks complicated, but the algebra remains the same. So we're not too concerned unless we have to do everything by hand. Okay, so all right, so this is you can decompose it, right? You can decompose my vector into the real and imaginary part, just like before. So in other words, the real vector, there are two real vectors. So 1, 2 real vectors. But one is kept real, and the other one multiplied by I make it imaginary. So once again, that's the real part, imaginary part. Okay, so then well, once again, that's what it might look like. So instead of combining here one component at a time, the first component, the second component, So the yes, first component and second component. Instead, we're combining real with real and imaginary with imaginary. Okay, so real and this is imaginary. Oh, so it's the same vector, as you can see, it's exactly the same vector, but we just rearrange the axes. So once again, green and purple, real, imaginary twice, or we do real, real, imaginary, imaginary. Same for numbers, we rearrange in a different way. So it's 2 and 1 and 1 and 2. Okay, so that's just if you want to visualize. Now, next, we have complex matrices. So 4 numbers, unfortunately, each is a complex number. Okay, so that's how it works out. You can do with vectors because we can't add real complex numbers. We can add complex vectors, right? So there is really no trouble whatsoever for us to, if I want to add 1 minus I, 2 plus 2I. How do I add? Well, there is no trouble. So it's a 3, 3. Okay, and here I have 1 plus 4I. Okay, so here's my ID complex vectors right away. There is really no trouble. So you do it component wise, you look at each of the components separately, you look at the real part combined with real, complex with complex. Yeah, I can multiply by numbers as well, so that's the challenge once again. So that's the thing about real complex numbers, they behave just like real numbers. And so that's why the whole linear algebra is constructed. So what we're doing here very timely is a kind of a little bit of a review of linear algebra. Okay, it's for the problem. Before we get back to differential equations, review of what we're looking at is linear algebra over complex numbers. So a matrix then is once again a function, but this time it's not from R2 to R2, it is from C2 to C2. Okay, so the complex plane to the other complex plane. So we're transforming a complex, not a complex plane, I'm sorry. C2 is not a complex plane, C the complex plane. Like this, once again, real part, imaginary part, right? And there are 2 of them here. So that makes it 4-dimensional. So the input is actually 4-dimensional and the output is 4-dimensional. So altogether it's 8 dimensions. But nonetheless, the definitions are verbatim, are the same. For example, what is the meaning of the determinant? It's the same. Okay, there is no trouble whatsoever to define. If the basic algebraic operations are available, so we don't have to change anything. So AD minus BC is the determinant of a matrix, even though it's made of complex numbers. So the output naturally will be complex. Even this is the same. The theorem that we had, whether or not we have a one-to-one function, or is it a singular? And the answer is determinant not equal to 0, complex determinant. And if it is not equal to 0, then you have a function that is one-to-one onto. The definition of an eigenvalue is identical. Once again, as I said, it's a little review. Identical definition. So verbatim, A of V is equal to lambda V. So in other words, that vector V is stretched under the linear operator, except it's not in the literal sense. So the imagination fails us here because multiplying by 2 stretches vector by 2. That's obvious what it means. What does it mean when you multiply a vector by I? Well, it surely is not pointing in the same exact direction. I mean, it does not. It does. It could, but generally speaking, it might hard to imagine what it looks like. Okay, so eigenspace, same definition. Once again, classification of linear operator. Let's take a look at what we already have seen. Once again, so we are scaling back and just look at the back to the real matrices, and then as we started with, so the discriminant of the Cartesian polynomial, it determines whether or not how many roots we've got, and so positive discriminant gives me, once again, remember this picture. Discriminant positive, have this, discriminant 0 is that, and finally this one is the discriminant is negative. Okay, so either we have a distinct real equal a real one extra point in, or we have two complex conjugate groups. Okay, so that's case number 2. Okay, so that's the last one. That's the only one we have to explain. Okay, so we'll just look at one example. Once again, back to this rotation 90 degrees. We already know what it is. I just want to carry out the analysis and confirm that the result that we already know about this linear operator is indeed our analysis of eigenvalues, eigenvectors will produce the correct result. Okay, so this once again, this is the experimentation produces these results. This is my, we already have found the eigenvalue just a minute ago, okay, plus or minus I, because of what the characteristic polynomial is. And then I am now to find the eigenvectors. This is the definition of the eigenvectors. Okay, so that vector xy, this is V that I'm looking for, is supposed to, under the operator f, supposed to produce a multiple of itself. But that multiple is I. Okay, so it's not a real number, so we don't expect stretching anymore, but it's multiplication by I, whatever that, it's really not that important what it means. Okay, so we just do algebra. And as every time we have done it, we end up with the same story. We end up with two identical equations. Okay, so because of this arrangement, the way it is defined, once we plug in, once we break our matrix equation at the top into the component wise equation, we have two equations to be satisfied simultaneously. But look at them; they are identical. Okay, it might not be easy to discover that these two equations actually are identical, and they do not look the same, but you see, why are they stay the same? These two equations.
Both sides by I.
That's right. Multiply both. Take the first equation. Multiply both sides by I. Okay. So what's going to happen? Y becomes well negative by negative I. How about by negative I? Okay. So if I multiply by negative I will get a negative I y, and on the right I'm going to have negative I x, and negative I times I gives you a y. Okay, so just like if you had, x plus y, x plus 2y is equal to 0, and I have 2x plus 4y is equal to 0. Once again, these are identical and these are identical. The same, except now where we have this luxury of multiplying by complex numbers too, but nonetheless, these are the same equations. And so then this is my eigenspace. Okay, and we can actually tell what that vector is. Here, x and y are complex, to be clear, x, y complex. And as we know, you cannot have both of them real. Okay, so then that dependence between two variable complex planes. So that's once again four-dimensional situation. So it is a some well, I don't want to say what it looks like, but easily to choose. If I choose, I just choose. Nonetheless, I choose x to be equal to 1, which makes me y equal to negative I. And then because there are always infinitely many eigenvalues, so I need to pick one, and the rest are multiples. Okay. And so if I choose x equal to 1, then y is equal to negative I, and then that's my eigenvector. And every multiple of that eigenvector is also an eigenvector, except multiples once again allowed to be. We allow to multiply by complex. Okay, so the second eigenvalue, it worked out exactly the same way, except the same procedure we go through as before. It just takes a little bit more. The difference is you have to be comfortable with complex numbers and carrying out these computations, but the plan is exactly the same. The logic is the same. The conclusion is the same, except all numbers that you have i's here and there appearing. So one I is the second eigenvector. So this one for I, lambda is equal to I, and here lambda is equal to negative I. Okay. So the rest are complex multiples of these. Okay. So then we know what it means. If you are a multiple of v1, okay, so if a vector is multiple of v1, then it gets multiplied by I. If it's a multiple of v2, it gets multiplied by negative I. That's what f does. So it doesn't, in these directions, they're not really directions if you think about it. Vector used to be a direction, now it's not really a direction because it is, what is it? I can't really explain it because it's, like I said, it's four-dimensional, and it is a vector, but because of the because of the possibility of complex numbers, it is two-dimensional. Okay, well, take one vector, it's still one single vector, so that's a single vector. And now if I were to take all the multiples, so say K V1, if I take the set, and K is complex. Okay, so vector V1 remains there. Okay, so so it's fixed, and then we take all of its multiples. Beforehand, when K was real, that was a line, that was a one-dimensional line, and here now, because we multiply by complex numbers, it's actually a plane. Okay, so that's the complexity in the imagination. It probably fails right around here. Okay, so over. So which means that so for example, as an example, let me take a look at it. So
Is it sorry, I don't mean to interrupt.
go ahead.
Is it like a square plane or a rectangular plane or
No,
more like a
it is
triangle?
an infinite plane, right? Because you can multiply by any number, just like you have an infinite line. The bigger number, they stretch more and more, and so it goes on and on. So it's a plane in the same sense as the complex numbers form a plane. It's like a complex plane hanging there, two-dimensional plane in the four-dimensional space. So all right, so then the idea of not rotating vectors is gone. Okay, so because multiplying by real numbers stretches in the literal sense. You multiply by complex numbers, and there, it's that analogy disappears, unfortunately. But that's what it is. That's what we're after. We are after. Remember, we even know what the answer we expect to have. We know this is rotation, so we expect a rotation. Okay, so so that's really what we have. So once again, if you have what is that the vector is. So once again, the multiplication by I or by negative I. So for example, if I have my vector is, so that, second, I don't have one picture here. Okay, so that's one vector, once again, one vector, which is this is my vector right here. This is this is my vector. Okay, so it has two values. It has its coordinates are 1 minus I. Hold on a second. No, it's this is my vector right on the left, and it is no, it's two components. Yeah, so this one is 1, and this one is a negative I. Right. So I'm taking my vector, which is 1, negative 5. Okay, that's my vector. In the first two pictures gives you only one single vector, and then that's my v, and then I multiply it by I. Okay, and then what happens? The first one will be I, and the second multiply I by I with negative signs, put 1, right? Okay, so indeed, as you can see, our vector was 1, negative I, it has become 1 I, and we say that 1 is a multiple of the other, and it is, but only in the complex sense. But nonetheless, I can mark the vector, let's say U. So this is my U right here. Okay, so it is indeed I, the purple one on the left, and a one green one, the real one on the right. So in other words, there's a shift from vectors that are the one in blue, that's V, and the orange one, that's my U. That's what has happened. It is surely a rotation, and the real part become imaginary and vice versa. Okay, so if we take only here what I did, I only took the real. I only took the real part. Yeah, so the real part. So this is real part of B right here, which is this 1, 0. I'm sorry, 1, okay, so that's the real V, and then I have produced the real part of U, which is, real part of U is 0, 1, right? Real part of V is 1, 0, okay? And the real part of U is 0, 1. Right, you see? So multiplication by I turn V into U, that's the whole computation is the top right. And then we remember suddenly that we don't really care about complex numbers that much. So let's concentrate on the real part of the input and the real part of the output. And the real part of V is simply 1, 0. That's the first vector over there, the pointing to the right. And then the real part of U is 0, 1, the one pointing in the positive direction. That's what you see here is what we have expected. We expect, as we expected, this is a 90-degree rotation. So the whole thing is 4-dimensional, as I said, but if we just take a slice of it, which is 2-dimensional, we see the rotation that we have counted out. Okay, you could ask yourself, maybe let me take a second. So if I take the imaginary part of V, what is it? Imaginary part of V is 0, -1, and the imaginary part of U is 1, 0. Okay. Okay, so then you can see that what has happened here is rotation, except, wait a minute, 0, 0, -1 becomes 1, 0. Hold on, no, 0, -1, 0, -1, this one. 0, -1 points this way. And then this one, 0, 1 is that. It's the same thing. It's once again rotation 90 degrees, right? So vector points down, now it points to the right. So it's still 90 degrees. Not that we care. Okay, so we really care about only about the real part. And we did confirm that if a vector is multiplied by I, at least its real part. So multiplication by I rotates the real part by 90 degrees. So that's what we have discovered here.
You can always rotate both parts by over 2, even though we don't really care about the imaginary part.
We don't, but yeah, it does. It does. So generally, I could have said that rotates the both real and imaginary part, and unfortunately, you cannot say that it rotates the whole vector because this vector itself is 4-dimensional. So you have to actually look at these two separately, and both of them are rotated by 90 degrees. Okay, so let's one more example. Let's take the general case of rotation through angle theta, and we see how that works out. So that's rotation in this theta sign, that is abstract. So we do a computation that we did before. This is my matrix. Okay, so we compute its characteristic polynomial right here. We end up with this characteristic polynomial. We set it equal to 0 and end up with, so I set it equal to 0 and solve. I'm using very freely my quadratic formula right here. And then as you can see, what actually works out is the discriminant is negative. So this is my discriminant right here, and it is negative because cosine is less than 1. Cosine squared is less than 1. You subtract 1, the whole thing is negative. Okay, so we knew that there should be no real eigenvalues for my rotation. So but we know how to handle it now. So this is we do not stop here anymore, because this is the new part. Is when you have a square root of a negative number, you just write I there. Okay, so here I actually did some simplification here, because 1 minus cosine squared. Remember that equation. Cosine squared theta plus sine squared theta is equal to 1, also known as the Pythagorean theorem. Okay, so to simplify things, I used the formula, ended up with sine squared theta. And once again, knowing how to deal with complex numbers, I end up with over here this -1 becomes I. So square root of -1 becomes I. So the end result is cosine theta plus I sine theta.
The coincidence is that's e to the plus or minus I think.
No, it's not a coincidence. Which we did just last time, right? Exactly. So this is, well, worth writing, E I theta. So E I theta, indeed, that's it is the same, pretty much, it is the same. So you might ask yourself, what is the meaning of the exponential function? That's the meaning of the exponential function. It is actually producing rotation along by theta. Okay, so these are the eigenvalues there. What are they? If you look at what do they look like? They have the same, they're complex conjugate, obviously. They are, the argument is theta. So that the complex number turns out our rotation produces a complex number with the argument of which is that angle. Okay, so not coincidentally, and I don't have a picture here, but if I were to plot these two numbers, where are they? Plus or minus I theta, so like this. So this is my theta. Cosine, this is cosine theta right here, this cosine theta, and this is sine theta, and this is negative sine theta. Okay, so the two eigenvalues that we have found, this is lambda 1 and this is lambda 2. They are complex conjugates. And so this is my complex plane. And as I said, so the theta is the angle, the argument as the terminology that we use. And incidentally, what's the modulus? What's the modulus? Remember what modulus is? So polar coordinates, rotation of the angle, and modulus is the distance. What's the distance?
The R.
Well, yeah, it's 1, right? So R is 1, right? So it's on the unit circle. So it is, because there is no stretching, there is no, that R is responsible for the stretch, and there is no R, so there is no stretching. We end up with nothing but multiplication by a complex number. So multiplying, so then everything is reduced to multiplication by this complex number, which you can write with cosine and sine, or you can write using the exponential notation, which is the same thing, only more compact. And then so everything works out as we just had. The example that I had a minute ago was rotation 90 degrees, and now it is the same story. Only rotation is theta angles. In this particular case, I believe this is picture specifically refers to 45 degrees. So rotation 45 degrees, and once again the complex, the real part is rotated 45 degrees, and then complex, the imaginary part also rotated 45 degrees. This is the rotation. So these are two vectors, and they are rotated, as you can see in either case. It's 5 or 12, 5 or 20. Okay, so this is 5. Actually, this is 504 that we care about. Okay, so all right, so okay, so I'm skipping this part when rotation is accompanied by stretching. So that's a combination of the problems, and that's when that R will play a role. So this is the if it's not equal to 1, we have a stretch, and the modulus is real. Okay, the modulus of a complex number is a real number, which means that the stretch will be also real. It's not complex anymore. So I'm skipping it, even though the computation is pretty much the same as we have done before. So the pictures are here. Rotation, you can see the rotation as well as the stretch. Okay, so the vector becomes longer. So I'll just jump straight to the classification. Okay, so that's the classification. We have a real matrix once again with two complex conjugate eigenvalues, which is what case we had. Then the operator does the following: it rotates the real plane through the angle theta. Okay, which happens to be the argument of the I don't think I did it right. Why is it sign here? Argument is the angle, okay? So the argument is the same because they're complex conjugate, the absolute values are the same because they're complex conjugate, and it is stretches or shrinks by the magnitude, by the modulus. So that's the modulus of those two complex numbers, okay, which happens to be one. So that's the classification in case number 3 of the cases that we have considered. And what remains really, once again, I'm skipping this and going to the point that we're trying to make, and that is not that. So it's a classification of quadratic of linear operators, and depending on where our complex numbers are, that's in the middle, it does different things. Okay, so once again, the equation that we're looking at is this. That is our characteristic polynomial. Okay, so except I replace lambda with x, and then it's a quadratic equation. And then it creates a dependence between P and Q, which is what that plane in the middle is. And so depending on whether a discriminant, that determines the discriminant. So discriminant is negative P squared minus 4Q. Okay, so that's the discriminant. The discriminant is this line over here. That line is a parabola naturally. And then on the parabola, the discriminant is equal to 0. Above above it, the discriminant is negative, and therefore the roots are complex conjugate. That those pictures supposed to indicate. Look at it, those two complex conjugate roots. Outside of that, or below the parabola, the roots are real, and therefore they lie on the real plane, but they can go either way. They're not dependent on each other in any way. Complex conjugates, as you can see, they're symmetrically located. And then so there are 4 cases. Roughly the complex conjugates, and then 3 possibilities. Either both of them are real, both of them are both of them are negative, both of them are positive, or one positive, one negative. And so each of which gives a different classification situation. Okay, so in case of a complex conjugate, there is a rotation with a stretch. Okay, that's what we just discussed. That's the top two possibilities. Depending on which way it goes, one case or the other case, we rotate clockwise or counterclockwise. We flip or do not flip the orientation. And then, as you can see, the case is when both of the both of the roots are negative, we have what do we have? We do not have any rotation. First of all, we have stretches along the eigenvectors. Red and green are the eigenvectors, and you can see what happens to them. They're being stretched, but also there might be a flip because both of them are negative on the left. There's a flip. That's what you see on the left. On the right, there is no flip. There's a stretch, but there is no flip. Okay, and finally, the possibility when both of them are one and one is positive, one negative. What does that mean? It means that the flip is incomplete. So when both of them are negative, there are 2 flips, as a matter of fact, and that's why it flips into the opposite side. And here the flip is only like this. That's in your image. So all of that's really not as much of a concern of ours, but rather what will that tell us really about the complex systems, or not complex, as a matter of fact, real valued linear systems of differential equations. Okay, so once again, depending on what roots of the eigenvalues we get. There will once again be 4 cases and different classification situations for our system, a linear system, and they behave quite a bit differently. And we already had a few ideas about that, so let's take a look at it to wrap it up. Okay, so once again, we're going to the matrix, but now we're looking at x prime is equal to f of x. Once again, everything is real. At this time is real, but the discriminant is negative and the eigenvalues are complex. Okay, so that's the case we haven't considered. And so let's look at this system. Okay, so we already know the answer, fortunately. We pretend that we do not, and then let's just conduct the analysis based on what we have already done. So my matrix is 1, negative 1, 0, 0, which we did last time, right? So that's my f. We write this as x prime is equal to fx as before. The matrix is 0, 1, negative 1. We know its eigenvalues are plus or minus I. Okay, so we already knew that. If we model do that's Euler. We do Euler, and we end up with a bunch of well, circles, and they are not literally circles, but they're cycles. Which you cannot be sure. Remember, we experimented with the predator-prey model, and it may or may not come back. We know that it goes all the way around, but does it hit exactly the same spot or not? You cannot tell from experimentation. So it does appear to be, as we can see, the colors don't match. So the upper half and bottom half plotted separately, so we do not assume that there's some connection between them and then necessarily will come back. But that surely is a prediction that we make. So once again, this is my characteristic polynomial. These are my roots, plus or minus I. We also know the eigenvector. That's where the analysis, where we hope to make conclusions here, is that we do the eigenvectors too, not just eigenvalues. Okay, so once again, we've done the job, and we have our eigenvectors. Remember this? So we did this today, the two eigenvectors. Okay, and so then what is the point? And the point is really that we could solve our differential equation very easily in that direction, in the direction of these eigenvectors. So f prime, x prime is equal to x. Well, let's put a v here. Okay, so that's the general equation. And now if we look at v, okay, so if this is v prime is equal to fv, which happens to be equal to, say, IV. Okay, so in other words, we're staying within one direction. If we were to stay in the direction of the eigenvector, which are also known as the eigenspace, if we stay within it, then what does my linear operator does? It multiplies everything by I. Okay, so we end up with this equation: v prime is equal to IV. Okay, so I'm not sure if you remember enough to write the answer. Ignore the fact that I is complex. What's the answer? The function, the derivative of which is a multiple of the function. E to the IT. Okay. That's my vector. Well, technically it would have to have two components, but nonetheless, because it's one dimensional, it's not, and here I have, say, I put here v1. Okay, so it will be multiple of v1, except multiplied by it, which is, as we know, is rotation by the angle t. And so the problem is solved at least within the eigenspace, and we can solve them separately within those two eigenspaces. Naturally, the real part is it's easy to write it complex, and if we were to go back to the real numbers, that things are become actually more complicated. As you can see, we consider in the real part, so from this exponential representation, we have to extract sine and cosine, which is what I'm doing here, to produce to tell us what's happening to the real part, and the answer is sine and cosine as we have predicted. And so the answer is then indeed the real part of that vector that we just discussed has cosine t sine t, and these are circles. This is a parametric curve. It's really a parametric curve, and parametric curve of that circle. All circles of the circles centered at zero, concentric circles. Okay, C is the radius. Okay, so and that's how to solve, and then that's exactly the same way it can be solved every time. As you can see, there is some work to be done because you go to complex domain and they come back, and so these two operations require some a bit of algebra. So I don't want to do that. I just wanted to produce the classification as a punchline. Okay, so the circles they look like this, bunch of circles. Now we can do that. Even though we knew that, and then so these are their terminology for it, and that's called the center. Okay, so we'll get to that in a minute, but this one, what we skipped last time, and we're skipping again. But what if my linear operator not only rotates but also stretches? Okay, so once we're skipping it, what's the end result? So in addition to pure rotation, what is there too is a stretch, which the end result is the periodicity is lost. This is what we end up with. So this is the vector. As you can see, the And that's what the Euler solutions look like. They don't come back, they definitely do not come back, and they spiral out away from the origin. Okay, so that's the differential equation at the top. This is matrix. You can go through through the algebra. This is my Cartesian polynomial. We compute the two complex eigenvalues, so they're not purely imaginary anymore, which means that there will be some stretch. And the stretch, as we know, comes from the rotation comes from the argument of our complex number, and the stretch comes from the modulus. So so the modulus of 2 plus 8i is in fact 4 plus 64 squared. So square root of 68. Okay, so it stretches by a factor of 68. And that stretch, every time you stretch more and more, you end up with, it's a positive number, larger than one number. So that's why we are moving away from the origin rather than towards. Okay, so that's, once again, I'm skipping these details and just quite a bit of details as a matter of fact, and just get to the classification. So once again, we have two way to approach. Well, there's the spiral either approaches the origin or runs away from the origin. Then in that case, we either describe it as a stable focus or unstable focus. So as you can see, so once again, this one has no arrow, unfortunately. So let me get the arrow here, but this one runs away. Okay, so it runs away, and so that's an unstable focus. So stable focus, so when we move towards it, and where does it come from? The answer is, how do we separate eigenvalues? Eigenvalues will tell you, and the center is the transitional edge case when everything is a cycle. So that's the classification. Let me put it forward. So the real part is once again complex conjugate. So that's a case 3. Remember, case 3, discriminant is negative. Okay, of the characteristic polynomial, you have two conjugate eigenvalues, and so then we have a focus when they're not when the real part is non-zero. We have a focus when it is 0. Okay, so we have a center. So a center, once again, circles or ellipses possibly when the eigenvalues are exactly imaginary, in which case there is no stretch, and then we have a center. Otherwise we have a focus, either stable or unstable, depending on whether or not the sign of the eigenvalues is positive or negative. Okay. So positive gives me unstable, and negative stable equilibrium. So this is the classification. Okay, so once again, we're looking at in the middle are the visualization of the two eigenvalues. Complex conjugate at the top when discriminant is negative, right? So this is discriminant is negative right here, and here discriminant is positive. On the curve, it is 0. Over here it is 0. Okay, and so then once again, when we have two complex conjugate, that's the case we've been considering. The end result is either focus or the either focus, stable or unstable. And then in the middle there's a center right here in the middle. Okay, so that's when they are complex conjugate, but the real part is 0. Okay, and then the cases that we have considered previously, when the roots are when the discriminant is positive, the roots are real. In which case we have a node, either stable node or unstable node, when both of them are on the same side, or we have a saddle. So remember, just to refresh your memory about if we were to speak of populations, then a certain combination of the population here is one population grows, the other one decays. Okay, that's what two, as you can see here in the middle, they are one eigenvalue is positive, the other one is negative, which means that once again the growth for one and decay for the other, and that's what you can see here, different behaviors for both of the variables. Both one good, the other one is bad, so they're back, so they're competing. And this is the opposite. They do the same. Either they run away on the right, or they decay. Both of them decay. So that's the case when the eigenvalues are have the same sign. Both negative, we have decay. Both positive, we have we have growth, which is incidentally exponential growth. Okay, so that's the classification of the eigenvalues. You can what eigenvalues supplies with. In high dimensions, it's not so not as easy, obviously. And so just think about if you replace the quadratic equation with a cubic equation, and so this classification becomes pretty hard to handle. Okay, so elementary algebra, matrix algebra, linear differential equations. So that's one of the reasons to study this elementary algebra of quadratic equations is that it opens up as we opens this door to the study of creating a theory of differential equations. Okay, so I don't want to go beyond this, so let me draw a line here to make it clear. So this is for the test, and then there's no test. Okay, so I have a few minutes left. So if you have any questions, so go ahead and ask. Otherwise, I might. So what's the big picture and what to expect on the final? So the big picture is big. Remember that we have where we started, and so the emphasis will be on the more recent stuff, but it's relies so heavily on dimension one, right? So even the existence uniqueness, remember, I remember that. The main idea, very important idea, and we didn't spend as much time, but fortunately it looks about the same in dimension two and in dimension one. So once again, continuity gives you existence, differentiability gives you uniqueness. So the problems will look like some of the problems in the tests, online tests. But the main difference is not really the nature of the problem, but rather how we present it, because you have to present it. So the main difference is that on one hand, the computer will not forgive you if you make a minor mistake in your answer. It's still wrong. Wrong is wrong. And here it's the opposite. But then because I will be evaluating the solution, not the answer. And so which means that a small mistake might be ignored, but on the other hand, you have to present your solution very properly and explain what's that you're doing, rather than just giving the answer. So if you have the answer and it's wrong, then there is even not getting any credit. So you have to be able to explain yourself, and pretty much if you know something, don't hide it, just say it and write it and explain it step by step, everything. Use scratch paper as much as possible, but don't try to keep it short. Don't try to edit it too much. The main points have to be hit in order to draw conclusions. If you don't remember the name, that's just like if you speak of some complicated issues and then the word that you do not recollect. I don't know, the word pandemonium. You don't remember you want to say pandemonium, you don't remember the word. Okay, so then you have to explain what pandemonium means in order to explain to the reader, what is that you have in mind. You see what I'm saying? So the words are very important because they help us, the definitions help us to communicate quickly and effectively, but it still happens when you don't remember the word. It doesn't mean that you stop there. You have extra work to do. You have to explain yourself. Okay, same with formulas. If the formula is not, you don't recollect formula exactly, then you have to recollect something and then explain what is that, what it might look like. Okay, so all right. So anything else about the final? Or what else I can add? Okay, so I'll stop here and then I'm still here. So if you have a question, ask one-on-one.